Today I'm presenting Automatic Parallelization of Software Network Functions, authored by Francisco Pereira, Fernando Ramos, and Luis Pedrosa, published at NSDI in 2024. So we'll walk through the motivation, the contributions, the methodology, and evaluation of their tool, Maestro. I thought this was a really cool topic because it's very much centered around the workings of networks, but I thought it was really cool to see how the things we're learning in this class are developed and applied across all different branches of computer science. So network functions like firewalls, NATs, load balancers, etc. Used to run on special appliances. Moving them to software on commodity hardware raises the question of how to achieve line rate performance. The intuitive answer is to parallelize across CPU cores, but naive parallelization can break NF semantics because these functions typically maintain per flow state. The authors argue that just as compilers handle low-level code generation, developers should be writing simple sequential network functions and then letting a tool automatically generate an equivalent parallel implementation. So parallelizing a network function has three main challenges. First, the developer has to understand exactly how state is accessed. So, for example, a firewall state is indexed by a symmetric 5-tuple across local area networks and wide area network interfaces. So second, once you know which packet fields index state, then you need to configure the NIC's, the network interface card's receive side scaling hash to guarantee that packets touching the same state always go to the same core. Finally, those are the first two challenges. And then finally, the third big challenge is that you have to write high performance code. You have to prioritize cache alignment, minimizing synchronization, and Maestro tackles all three of these in an automated fashion. So Maestro is built on two fundamental observations. First, many DPDK-based NFs already have separate stateful operations in well-defined data structures. They are already separating them. So this allows exhaustive symbolic execution to extract a precise model of how packet fields map to state accesses. Second, once you know exactly which packets touch the same state, then you can encode that as a constraint and use an SMT solver to derive RSS keys that guarantee these packets get pushed to the same CPU core. So with these two insights, Maestro can automatically generate parallel network functions that preserve the original semantics. So to summarize the paper's contributions, first, Maestro itself. So it takes a sequential network function and outputs a parallel version. That's pretty huge. Second, the symbolic execution pipeline that extracts exactly how state is accessed. Then there's the code generator that emits both shared nothing and read-write lock-based versions, complete with cache alignment and NUMA considerations. And finally, the authors evaluated Maestro on 8 real DPDK network functions and found excellent scaling and outperforming even hardware transactional memory. So here's the high-level architecture of Maestro. So first, KLEE drives an exhaustive symbolic execution of the sequential network function to produce a complete symbolic model. Next, the constraints generator analyzes that model to find for each pair of packet inputs whether they must go to the same core, the flow constraints, or Third, so the RS3 takes those, RS3 is a library they built for this, it takes those constraints and it formulates an SMT problem encoding the Toeplitz hash function. It solves for RSS keys per network interface card interface. And finally, the code generator emits a C implementation that sets up DBDK, configures RSS, allocates per core state, and then either creates independent shared nothing replicas or inserts optimized read-write locks if the shared state is just completely necessary. So KLEE's exhaustive symbolic execution produces a tree of all possible packet processing paths, where packet headers, like source or destination IP ports, are symbolic variables. So whenever the NF performs a map put or map get, whenever it accesses something with the per flow state, Maestro records it in a stateful report, or SR, including the symbolic expression in the key. So that stateful report is the basis for discovering which packets have to stay together. After collecting all the stateful operations, Maestro applies these 5 rules to decide how state can safely be shared. So rule 1 is straightforward. If two map calls use the same key expression, we must send those packets to the same core. Okay. Rule 2 says that if one operation only inspects a subset of packet fields, like just source IP, whereas another uses a full 5-tuple, then we're going to pick the subset because it implies the same core assignment. R3 and R4 detect unsatisfiable sharding patterns, so two independent counters by source IP and destination IP are impossible to shard via RSS. It'll detect that. And then R5 is just a simple heuristic. If the network function's correctness is equivalent when sharding on field A or field B, choose the field that the network interface card's RSS can actually hash. So, once the flow constraints are known, RS3 formulates a set of SMT clauses that say the following. For any two packets satisfying C, D prime, their toplets hash outputs must be equal, which means they will land on the same core. For N interfaces, you get constraints involving keys K1 through Kn. So to avoid pathological keys that only differentiate two cores, RS3 also adds soft constraints, which is just a partial maximum satisfiability problem, encouraging as many key bits to be 1 as possible. So ultimately, RS3 produces one 52-byte toplets key per interface and the set of packet fields to hash. Maester's code generator inspects whether a fully shared nothing sharding is impossible. And so if that's possible, it emits code that does the following. It sets the RSS on each network interface card according to the RS3 keys, the keys generated by RS3. It allocates each data structure separately per core, cache-aligned, reduced capacity per core to preserve global memory footprint. And then each core loops on its RSQ without locks. If shared nothing fails, say that NF just uses a global counter or has MAC-based lookups that RSS can't shard, Maester is going to fall back to a lock-based design. It still uses RSS to balance the load, but now all cores have a shared state. So to optimize this, it installs per-core spin locks for readers and global barrier for writes. Readers only take a local spin lock. Writers lock all cores spin locks to serialize writes. So a few practical challenges arose in making Maester's outputs performant. First, the naive RSS key from the SMT solver might lead to only two possible hash outputs, which would just overload two cores. Maester uses a partial max-sat procedure, like I said, to force as many key bits to be 1 as possible, and then it resolves to spread flows evenly. So second would be that on dual socket and UMA server, the network interface card lives on one node. So by pinning packet buffers to that node's LLC and keeping state local to the core socket, we minimize cross-socket traffic. Third, real-world traffic exhibits a Zipf-ian skew. So if hot flows all hash to one core, that core is going to be saturated and it's going to get overloaded. Static RSS++ balancing, which involves swapping and direction table entries, partially alleviates this, but it's just a problem that exists. Networks are going to have heavy flows sometimes. And then the fourth challenge is that sharding state across cores reduces each core's working set. This improves L1 and L2 cache residency. That's a good thing, obviously. It boosts the throughput beyond pure parallelism, and that's great because it's just swifter. But as you can see, we're going to be talking about how later that doesn't introduce a slight security risk. So finally, for lock-based code, maintaining per-core aging metadata allows read-only packets to proceed lock-free, and then only when a flow truly expires do you acquire the global write lock. So that's how they sort of optimized for the slightly lazier lock-based system. So to evaluate Maestro, the authors used a standard two-machine DBDK testbed with a top-of-rack switch in between. So both machines have dual Xeon Gold 6226R CPUs and Intel E810 100 gigabit per second network interface cards. The traffic generator replays PCAPs via DBDK packet gen. So they run 3 sets of experiments. A packet size sweep to determine maximum no-op throughput, which reveals the PCIe bottleneck at around 90 Mbps. A churn study on the firewall comparing shared nothing versus lock versus just regular transactional memory under various flows per minute, and a uniform small packet workload over 8 network functions, which are the forwarder, bridge variance, policer, firewall, NAT, connection limiter, port scan detector, and load balancer. They measure throughput, loss, and tail latency with a 0.1%, less than 0.1% loss threshold. So this plot summarizes throughput versus core count for each network function with 3 parallelization strategies. Wherever a shared nothing design was possible, like FW, NAT, or PSD, it scales linearly to the PCIe or one-line rate limit. And that's good. It's good for this system. So the lock-based versions also scale, but hit limits way earlier, especially when writes are frequent. Hardware transactional memory is an appealing idea in theory, but in practice, abort rates just kill performance on stateful network functions. Only trivial network functions like no-ops or static bridges can use transactional memory effectively. In short, shared nothing is the clear winner. Locks are acceptable as a fallback, and transactional memory is simply impractical for NFs. So VPP is a widely used performance framework, high-performance framework that processes batches of packets in a shared data set. But it requires developers to write their network function in a VPP idiomatic style. So they have to get customized with it in order to use VPP. The authors compared their automatically parallelized NAT against VPP's NAT44EI. And here's what they found. They found that even though VPP is highly optimized, Maestro's shared nothing NAT outruns it, hitting the PCI limit with only 10 cores versus VPP's about 70 Mbps at 16 cores. This demonstrates that automated semantics aware parallelization can rival or exceed hand-tuned batch-oriented frameworks. They have this capacity. I feel like that's a huge takeaway from this, is that these automated parallelization techniques can actually match in certain circumstances. And here's some of these circumstances. So Master is not a silver bullet. For ESC to work, the NF code must conform to certain conditions. State must only be known. State only in known data structures. Loops must be bounded. No pointer arithmetic can exist outside those structures. And so that excludes a lot of legacy network functions from being parallelizable with Maestro. So also RSS can only hash certain header fields. So if a network function indexes state by a field RSS can't hash, like a dynamically learned MAC table or something, then shared nothing is impossible, and Maestro just has to fall back to locks, which, as we showed, is way less efficient than the shared nothing model. So finally, sharding can be attacked, and we talked about this before. It's great that sharding allows for improved L1, L2 cache usage, but relying on that so heavily means that an attacker could craft like a bunch of flows that hash to the same entry, and then would obviously overload that network function, crash that core, just classic distributed, or not even distributed, just denial of service attack. So yeah, this is why randomizing keys for RSS is crucial, and that's what they do, but it's just sort of like it's not a catch-all, it's still a problem. So future work, I think, has the potential to include probably supporting programmable network interface card hash functions, maybe integrating full RSS++ rebalancing, and extending to eBPF network functions. In general, it's a system that works. It's really cool to see a system that is parallelizing existing code automatically, and it's doing it well. It's doing it in a way that is surpassing a lot of existing solutions when it can get to it, and that's not all the time, as we've seen. So I think this is going to have an impact on the field. It was written relatively recently, and it'll allow developers to write simple sequential network functions and just leave the rest to Maestro, or at least it's a proof of concept. Thank you very much, and that is all.